All right, greetings, folks. We are about to begin our lecture on the nervous system. I was trying really hard to figure out how I wanted to cover this system, and I had looked at a few crash course videos, which is what we have been doing for the last couple weeks, and ultimately I actually thought that those were diving a little bit deeper than we had time for, since we only have a month left of school. So I decided that I was going to take the lecture that I did in class and abbreviate it some. And so this lecture I will be doing myself, and we'll still have some activities and stuff that go along with it. So I hope that you find this time valuable. Speaking of making the time valuable to you, I did want to let you know that I normally do have several videos and commercial breaks throughout, but I did get rid of those for the sake of honoring your time commitment to this class. I didn't want to throw stuff that wasn't necessary at you, and I figured you can always find some things that will make you laugh on your own. So I hope that you find that that the time spent here with me is meaningful. All right, so we're going to do a deep dive into the skeletal system, and the way that I wanted to start is actually by talking about some similarities with deep dive into the nervous system. See, I already got ahead of myself. The way that I wanted to start with some similarities between the nervous system and the skeletal system, which we covered 2 units ago. And you might remember the skeletal system, we broke into the appendicular and axial skeletons, where the appendicular skeleton was essentially that of the limbs, and the axial skeleton ran skull, cranium, all the way down to the pelvis. And the true is actually very similar for the nervous system. So we do have 2 branches for the nervous system. The main portion, which would be similar to our skeletal system, runs the y-axis of the nervous system as well, and that's called the central nervous system. And that central nervous system is indeed made up of the brain and the spinal cord, right? And I want you to think of the central nervous system as you would think of the motherboard and CPU of your computer. Now, I don't know how tech savvy or tech centric you all are, but the motherboard and CPU are essentially what allow your computer to do everything that your computer does. Your computer can be limited by other things like RAM and the speed of your hard drive, but ultimately the tasks that your computer carry out are processed in the central processing unit, the CPU. And the brain and the spinal cord do the same thing for your body. So think of the central nervous system. Make the analogy to your CPU, all right? Now, on the other hand, you have ways of getting that input to the CPU on a computer, and the same is true for your body. So if we're thinking of like a keyboard, or right now I'm moving my mouse on my iPad here, and you can actually see this little dot moving around on the screen. The trackpad that I have my finger on that's moving it around would be my input device. Now that could be analogous to your eyes, right? My eyes are my input device for everything that I see. My skin is my input device for everything that I feel. My ears are that for hearing or sounds, right? So the peripheral nervous system is really the nerves outside of the brain and spinal cord that bring those input stimuli to the central nervous system. So we need these to be working in coordination with one another in order for our nervous system to really function the way that it should, okay? All right, so the next thing I want to dive into, now that we talked about the central nervous system and compared it to the peripheral nervous system, is the main functions of the nervous system. The first of which, of course, just like the CPU of your computer does, it's just to control your body. Just like the CPU controls really everything that your computer does, the central nervous system, or your nervous system in general, controls your thoughts, your actions. And those thoughts and actions are often the result of stimuli, our second function. So there are a whole bunch of different stimuli that we could be talking about. I'm trying to bring up my pen here. Sorry about that. See if I can change the color. Let's go with, I'm thinking maybe we'll go with red. So there's all sorts of different stimuli that we could be talking about here. And that's anything from like sounds, right? We could have even pain or temperature. All of these things are things that your body is going to adjust to and respond, right? If I hear a loud sound like that, right, I might get scared. If someone goes to punch me in the face, right, before their hand hits my face, I'm going to close my eyes rapidly as a result of both seeing it and maybe hearing them scream obscenities at me, right? All of those are stimuli. Now, I'm trying to think of some other examples off the top of my head, right? You hear a loud sound like I just said, or, someone slaps you. That was the pain one. Temperature kind of makes sense, right? If it gets really, really cold, my nervous system tells my muscles to start shivering, right? It tells me to get up and move, to warm myself up. All of those are just different forms of stimuli. Now, we can respond to those stimuli in two different ways. If that noise that I just made on the table here scared you, you probably didn't choose to be scared, you just were scared, and that's an autonomic response, right? That's a voluntary response. On the other hand, you could have somatically responded, or you can somatically respond to things, and that's choosing to respond. So if you are choosing the action that is responding to the stimulus, that is called a somatic response. All right, let's move on here to a nerve cell. So a nerve cell is probably going to be the crux of what we talk about today. And a nerve cell is called a neuron. And the way a neuron works is actually absolutely amazing. And all of the things that your body is capable of doing, you can really thank a neuron for. So a neuron is an incredibly specialized type of cell, similar to the way that all of your cells are specialized for whatever their physiology is. Their anatomy has to be specialized in that sense. So that's what we're going to talk about now. So the question on the top of this slide says electrochemical impulses are able to travel through the body at nearly the speed of light, right? If I were to stub my toe on the corner of the table that's in this room with me right now, it would have like almost instantly my toe would start to throb, right? And it would feel painful, and my body would be saying, hey, what you just did, not cool. Maybe let's try to avoid that table in the future, right? Pain is actually a very important response to tell you what is bad for your body, right? If you are in pain, you probably should stop doing whatever it is that you did. And how does that happen so rapidly, though? How is it that almost instantly when I stub my toe, do I actually feel the pain? Because that impulse has to travel up to my brain. My brain has to process it as pain and send it back to form, that physiological response that says, hey, what you just did was not cool. How does that happen so quickly? So we're going to talk about that. So in order to talk about that, you really need to know about the structure of a neuron. So there are really two main parts to the neuron. There is this bald end right here, and then there's this tail. So the tail runs all the way this way. The tail is called an axon tail. Most of you guys have probably heard of this already in other classes. The bald end right here is called the cell body. Now, let me just explain what the function of a neuron is, and then I think it will make a little bit more sense. Its sole job is to move electricity. So think of it almost like a power line outside on the street that's moving electricity either to your home or from your home. What the cell body does is it pulls electricity in. So I'm actually going to change my pen color here. So electricity is what's shown on these arrows. This is electric current. So you'll notice that electric current, which is really just the movement of electrons, right? Which is why I drew the little E with a negative sign, because an electron is essentially just it is negative. I'm trying to figure out how I explain it, like electrons versus protons, right? It has a negative charge, I suppose, and it's the movement of that negative charge from one place to another. That's all electricity is. Hopefully you guys remember that from Mr. Jansen's class. But it gets pulled in through these branches. And these branches, I'm going to change my pen back here. These branches are called dendrites. So these dendrites pull in electricity. It gets concentrated in that cell body, and then it shoots down the tail. Now, you'll notice that there's actually a second tail right here. Now, what I will say, I'm going to erase that, is not all neurons have a single tail. Some of them have two tails. Some of them can have three tails. Most of the time in pictures or diagrams, you see one tail just because it's a little bit easier. Kind of like when we talked about the cell, they typically show a single nucleus and maybe just one Golgi body. But ultimately, there can be many multiple organelles per cell, just like there could be multiple tails on a neuron. It's just kind of how electricity needs to be sent. So the important part is we need to move electricity down this tail though, and we want to move it very, very quickly. So the tail is actually structured quite uniquely. You'll notice that most of the tail is wrapped up in actually smaller cells. So we've actually got the giant neuron that's taking up this whole slide, but that giant neuron has little cells of its own. Think about like a whale that's swimming through the ocean that has these little barnacles on it, right? This little symbiotic relationship. That's kind of what's happening with your neuron. Your neuron is a cell that has smaller cells that live on it. And those smaller cells are called Schwann cells, named after Theodor Schwann, the German physiologist. And Schwann cells are mostly made of fat. And a specialized fat called myelin, sheath. And that fat is really, really important. I want to talk about that in just 1 second. But the other part of the tail that we haven't yet talked about are these naked sections. You'll notice that there are portions of the tail that have no fat on them. There's no fatty wrapping or cushion or insulation on it. And that was discovered by a French scientist by the name of Ranvier. So these are called nodes of Ranvier. And then finally, the end of the tail has additional branches, kind of like our dendrites, but not quite as pokey. These things right here, and these are called axon terminals. All right, so the question remains, again, how is it that electricity moves down this neuron so rapidly? Well, it moves down this neuron so rapidly because of Schwann cells. As it turns out, electricity does not, let me change my pen one more time. Electricity does not travel through the, oh, I'm sorry about that. Wish I could undo that. Well, that's fine. I'm just going to leave it. Electricity does not travel through fat. There's this common adage, what is the fastest way to get from point A to point B? So let me write this down. So what's the fastest way to get from point A, right here, to point B? Right here. And most people would say a straight line, right? You go from here to there. That's the fastest way. If you were to dip down here and go over there, whoops, sorry, I didn't want that to pop up yet. That's a little bit longer of a path. And normally, right, the straight line theory is correct. That is the fastest. But electrons cheat. Electrons can do what nothing else on the planet that we know of can do, and it can quantum leap. And what that means is, instead of going from point A to point B in a straight line, let me grab my handy dandy little eraser here, right? What if we literally were at point A, and instead of traveling in a straight line to get there, we were immediately in the next moment in time at point B? All right, what if we essentially could travel through space and time, almost like a wormhole? Electrons, believe it or not, can do that. And they can do that with the help of fat. So since electrons can't travel through fat, right, as an electron, I'm going to try to change my color here one more time, right? As an electron is traveling down, do you guys see me up here? It's traveling down and it spots itself right there. It's going to jump over the Schwann cell, and it's going to be immediately there. And then at the next moment, the Schwann cell is there. And at the next moment, it's there. So that is the trick. That's what I have popping up here, right? Electrons can quantum leap over myelinated portions of the neuron. And that reduces the length that that electricity has to travel immensely, right? We're talking, look at this tail and tell me how much of that tail is actually naked. How much of that tail is actually these little nodes? Almost, like maybe less than 5%. So we're taking a journey that is incredibly long from toe to brain, right? If I'm going back to the whole stubbing my toe instance, and we're shortening it that much, which is just absolutely amazing. All right, let's move on a little bit, and let's talk about, once we get to these axon terminals right here, how do I get from one axon terminal to dendrites on the next neuron? Well, we actually use something called a synaptic juncture, or a synapse. So in this picture, what you're actually seeing is that synapse. So you're seeing right here, this is an axon terminal. And that means that this right here is a dendrite. Now, here's what stinks. You can definitely tell that the electrons are flowing from here, right? Because it actually shows it almost as a lightning bolt. What really stinks, though, is that electrons, even though they can travel over Schwann cells or those myelinated, or they can essentially effectively jump those myelinated sections, shortening the movement along a neuron, they cannot jump from one neuron to the next. It's almost like it's too much. If you guys remember, these cartoons were really popular when I was little. Maybe this is like a okay boomer statement of me, but I still remember those Wile E. Coyote cartoons from when I was younger, how Wile E. Coyote would be chasing Roadrunner and then run off of the edge of a cliff, right? And then realize, oh crap, I'm off the edge of a cliff, and then you just see him drop, right? He'd be floating there off the edge of the cliff, he'd turn around, and, oops, oh well, and then he's gone. That's kind of what an electron would do. An electron can't make the jump from here to here, so it's got to get converted into a chemical instead, and that is what you're seeing in this picture. These little balls, so to speak, are called neurotransmitters. I'm sorry about that. I'm going to try to erase that and start again. These are called neurotransmitters. And they're exactly what they sound like. They're transmitting the impulse from neuron to neuron. So essentially, they are taking the electric current, converting it into a chemical like acetylcholine or like dopamine, and then that can move across the axon terminal to the next dendrite, and then it's being converted back again into an impulse. And that happens over and over and over in fractions of seconds to get to the brain and all the way back to my toe. And then boom, my toe is throbbing in pain because I stubbed it. I just think that's absolutely amazing. And just, I don't know, explains a lot when it comes to different disorders like Parkinson's. So, okay. So the last thing that we're going to talk about here today is the central nervous system. I'm going to talk just about the lobes, and then we're going to save the rest of the lecture for a little bit later this week. So before we get to lobes, I did want to talk about some of the other major coverings and whatnot to the brain. The first of which, so if we're looking at this picture right here, you're going to notice that the brain is not exposed in your skull cap, right? It's actually wrapped up. It almost looks like there's some saran wrap on it, but there's not just one layer of saran wrap. And actually, it's not just your brain. Your spinal cord has this as well. It's quite amazing. These are called meninges, and these meningeal layers, you actually have 3 of them. So I'm going to label them in the picture, and then we're going to talk a little bit about them. So in this picture, you can actually see, right, your skull, right? This would be the bone, which would mean that these two right here and here is just bone skin. You might remember that that's called periosteum. So then we have these 3 layers, right? We've got 1, we got layer 2, and we've got layer 3. So let's talk about layer 1 first. You'll notice that layer 1 is by far the thickest, and it is the most protective layer of the brain. It is called the dura mater. And the dura mater actually comes from the Latin meaning tough mother. And I'm assuming that was named because, mothers are thought of as very protective over their children. So since this layering of the brain has that same function, we call that tough mother. Now, number 2, you'll notice it's got all these little tentacles and it almost looks kind of creepy like a spider. And for that reason, we call that layer the arachnoid. The arachnoid layer, the spider layer. And then finally, there's the very thin layer that's blue in this picture, and that's called the pia mater. The pia mater. And the pia mater is, if you were to ever see a brain Even after it's been removed from its skull cap, the pia mater will still be attached to the brain, right? It's a very, very thin, again, like a saran wrap type of layer, but it's a very, very thin layer that's like permanently on the brain. So those are the three coverings. So what is the point of these coverings? Well, first and foremost, there is some fluid that's contained within these coverings. So between the pia mater and the arachnoid, right in this area right here, I don't know if you can see that. Let me change my pen color once, maybe to this greenish right here. So in this area that I'm coloring in, that I'm shading in with that green, you have a specialized fluid called cerebrospinal fluid. And if you take a look in the corner, up in the corner up here, you can actually see this animated GIF showing the movement of this cerebrospinal fluid in the brain. It's quite amazing. This fluid has a bunch of purposes, but there are two primary purposes. The first of which is just to add buoyancy. If you think about it, your brain is actually 2% of your body weight. So let's just pretend that you're a 100-pound person, which, congratulations, I can't imagine being that light. But if you weigh 100 pounds, that means that your brain is 2 pounds. That doesn't sound like a lot. But your brain also is fed, you can't see that in this picture, but it's fed nutrients through like the carotid artery. And the carotid artery is not a very big blood vessel, right? We're talking pretty darn thin, maybe the thickness of like the point on a like a number 2 pencil. And even 2 pounds sitting on a blood vessel would pinch it off, almost like, standing on a hose after you turn the hose on, right? You're going to almost kink it, and you're going to prevent water flow. If you're preventing blood flow to the brain strokes out, right? It runs out of oxygen. So what happens is, as you know, similar to you, if you were to jump into a swimming pool, you weigh less in a swimming pool. That's why astronauts, they train first in water, because you can jump and like slowly float down because you're more buoyant and stuff in a swimming pool than you are on land. So the same is true for your brain. We essentially float your brain in your head to make your brain lighter than it actually is. It actually weighs less in your head. It has the same mass, but less weight, which if you've taken physical science, hopefully you remember the difference between mass and weight. The other thing, though, that the cerebrospinal fluid does is it protects your brain from electric shock, which is actually quite amazing. If you were to take like a coin and try to shove it in an outlet, especially an older outlet that doesn't have, GFCI circuitry and stuff in it to prevent shocking, you could probably kill yourself, but you're unlikely to kill yourself because this layer of cerebrospinal fluid sort of insulates your brain from that electricity hitting your brain and again, causing irreparable damage. So interesting stuff, I think. Your brain has a lot of demands on your body. It has a lot of demands as far as blood supply, oxygen, and glucose. Remember, it only weighs 2%. It only represents 2% of your body weight. But when it comes to blood supply, it's taking a whopping 15% of all of your body's blood is tied up in your brain at any given time, because it is always working. Even when you're sleeping at night and you think that you're resting, your brain is using up a ton of energy. And actually, I'm going to get to that on the last bullet point here when I talk about glucose. It also uses a lot of oxygen. 1/5 of your body's, or 20% of your body's oxygen is used up by your brain. And then lastly, I was just talking about energy supply, 1/4 of your body's energy supply. Remember, no matter what you're eating, your body ultimately is relying on glucose for energy, and 1/4 of that is locked up in your brain at any given time. By the way, the reason I have this baby yawning here is because that's why we yawn. If your brain isn't getting the 20% of your body's oxygen supply that it needs at any given time, you yawn. And the contagious yawning thing is just, I think, an evolutionary thing, where if you see someone else yawning, your brain probably tells you autonomically, hey, that person's running low on oxygen. Maybe I am as well. Maybe I should be yawning. That's why you yawn contagiously. It's an evolutionary safety thing. So pretty amazing. All right, so the last thing that we're going to do in this first part in our series here is to talk about the 4 lobes of the brain. So we've got the frontal lobe, the parietal lobe, the occipital lobe, and the temporal lobe. So I'm going to start with the frontal lobe. And what I want you to know about the frontal lobe is that it essentially handles these 3 things: speech, movement, and personality. Now, the other thing that you should know, I did have that come up. There is a video that goes with that, but it's not going to work, folks. I'm really, really sorry about that. Yeah, it's not going to work. Darn it. And they won't even let me get rid of it. All right, can I get this to go away? Okay. I'm so sorry, folks, because I can't, it won't let me listen to the video. This video is actually quite interesting. You could try looking it up on YouTube. It's right after or during the Grammys several years ago. This woman literally goes into a case of word salad. I can't get this to go away though. Ah. You know what? I'm going to try to relaunch this. Maybe I will delete it for now. Okay. I am sorry about this, folks. By the way, this is like the third take of me trying to record this video, so it has been nothing but problems. From current, come on, work for me. Oh, gosh. All right, I'm really sorry about that. So the frontal lobe deals with speech, movement, and personality. It is the most evolved lobe of the human brain. You'll notice that the biggest differences between us and some of the other higher primates is, we have much greater range of speech. Our personality is significantly varied, and we're able to move with much greater dexterity than other primates. On the other hand, we have our parietal lobe, and our parietal lobe is all about processing essentially what's coming from our skin, so pain, pressure, temperature, touch. By the way, the frontal lobe is also going to be dealing with smell, but we're going to talk about that later. So we've got smell here. We've got mostly skin being processed here. We've got our temporal lobe, which is processing mostly stuff involved with hearing, so sounds and tones and loudness, but it also helps us with memory retention. I don't know if you guys have ever seen the movie Simon Birch, but that movie actually does a pretty good job. In that movie, Simon Birch actually hits a baseball. Well, he ends up killing his mom, so actually that's a really bad example. But I know that there are examples where people take blows to the side of their head and actually suffer memory loss. Oh, there's another movie, Memento. Obviously, that's just a movie, but it's based off of true events. Another story it's called Paprika. I think it was a European film based off of true events of someone that had memory loss due to physical damage to their temporal lobe, which is kind of amazing. And then finally we have the occipital lobe, which is the vision center of our brain. So it's interesting because our eyes actually pop out right here, right? But our visions aren't processed until the back of our head. Quite amazing. So I am really, really sorry that I ended the presentation this way. I don't know how to get out of here. Come on. This is the one downside to recording my own lectures, folks, is I'm constantly making mistakes, and then I try to re-record them, and I don't get better when I start over. So that's going to be it for our first little piece of lecture here. So if you have any questions, please feel free to reach out. Otherwise, thanks so much, and I hope to see you guys around during office hours. Take care. Bye.